All right, let's talk about power series some more. This is sort of what we're going to be talking about for the rest of our time together. Um, Power series some more. I just want to do one more example of finding the radius of convergence of a power series. Power, I wrote wrong. Radius of convergence. Remember we had a theorem last time, I don't know if you remember, that said every power series has what we call a radius of convergence. So a power series, this was the theorem, and the second time I've written power with a RE at the end. A power series has a center and radius of convergence, so that it's always the case that there's always some sort of number in the middle, and then the convergence, the x's for which the series converges, lie in some kind of interval. And the only thing that's a little uncertain is the endpoints of that interval. The interval may include both endpoints. It may include one but not the other, or may include neither of the endpoints. But every power series has a center and a radius of convergence, which means the convergence occurs inside an interval. Oh, they're telling me. Sorry to the folks at home. I was muted on my Zoom. Thank you for somebody who put that in the chat. I'm talking here. I'm talking about power series. A power series has a center and a radius of convergence. I hope you can hear me now.
Probably. Yeah, we can hear you.
All right. Thank you. Sorry about that. Now, how do you find the center and how do you find the radius of convergence? The center is actually very easy to find. So the center, let me say it this way, a power series like, if I have the sum Cn x minus a to the power n, remember a power series that looks like this is called the power series centered at A. So this is how you find the center. It's just that number, A. So a power series like this has center A, all right? A typical power series, most of the examples we do don't even have the A there. That would be centered at 0. So if it just looks like the sum Cn x to the power n, this is centered at 0. So when you see x minus whatever, that number is the center. What if it's a x plus? That means the center is a negative number. So something like if it were the sum of, Cn, but then like x plus 2 to the n, this is centered at negative 2. Right? Anyway, finding the center is simple. You just got to know what to look for. Finding the radius of convergence is quite a bit more complicated. To find the radius of convergence, sorry, I got a ding. My dear wife is texting me. To find the radius of convergence is quite a bit more work, but for at least for the examples that we're going to do, we use the ratio test. We did a few examples of that last time. I just want to do one more to start us off today. Make sure everybody is hip to that. To find the radius of convergence, we use the ratio test. Let's try it out. How about, let's do an example. The sum n over 4 to the n, x plus 3 to the n. All right? I would like us to find the center and the radius of convergence. The center is simple. What do you think? Somebody want to tell me what's the center of this power series? Negative 3, he says. I agree. It's just, you just look at, this number right here. If it says x minus, then that number which is being subtracted is the center. When it says x plus, it means x minus negative 3. So the center is, x, Still getting used to my new app here. The center is, come on now, -3. Ah, I did it again. Sorry. I actually have like a silk glove, which is meant for doing what I'm doing so that you don't accidentally hit a button with your finger while you're writing with the pen, which I thought of wearing, but I don't know. I feel like I'm not the kind of guy who wears a silk glove, one glove in public. Maybe. Michael Jackson. Yeah. I don't know. I'm thinking about it. I have some personal issues to work through if I want to wear a glove like that in public. I could get 2, yeah, I guess. A Luke Skywalker style. He's only got 1, right? Okay, let's see if we can find the radius. That's the more interesting part of this. Radius. You do the ratio test, which is that thing about the L. The L is not equal to the radius, but it's very closely related. I'm going to do lim n goes to infinity, absolute value, a n plus 1 divided by a n. Right? Remember that thing? Let's do it. I'm going to go down here. I hope I can keep this on the screen. So the L is going to be lim n goes to infinity. All right, absolute values, which hopefully won't matter much at least. I'm going to go a n plus 1 first. So that would be, I am reading the original formula in the series, but replacing all the n's with n plus 1. So it's going to be n plus 1 over 4 to the n plus 1 times x plus 3 to the n plus 1. All right? That's a n plus 1, and then divided by a n. Would you mind, as I always do, I'm going to do, instead of divided by, I'm going to do times the reciprocal of a n. Come on. So I go times now, 1 over the original thing. So it used to say n over 4 to the n. It is now going to say 4 to the n over n. And then I guess that x plus 3 to the n needs to be in a denominator. So I'll write it as 1 over x plus 3 to the n, right? That's the reciprocal of the original formula. Okay, this is a n plus 1 divided by a n. And now we simplify. So you sort of put together the things that go together. So I have powers of 4. I'm going to say lim. First of all, can we talk about the absolute values? What effect do the absolute values have on anything? Everything inside there that I see is positive, except perhaps x plus 3. We don't know what x is, so that part might be negative. And so those absolute values really can just kind of push into everything, and they will remain around the x plus 3s, but nothing else. So just doing that. Once you get used to this, you can probably do several steps at once, but just doing that one little absolute value thing. The absolute values can push past everything all the way down, but they do have to stay around x plus 3 because x can be positive or negative, so we don't know what x plus 3 is, positive or negative. All right, let's simplify things. What remains when I combine the 4s? I got 4 to the n in the numerator, 4 to the n plus 1 in the denominator. That means we have 1 extra 4 in the denominator. So those 4s will come together and give me, they will cancel out and end up with a 1/4. I have an extra 4 in the bottom. All right. The ends don't really cancel in that sense, but I mean you can put them together. You get n plus 1 over n, and when I take the limit as n goes to infinity, that's going to go to 1, just like it always does. You know, we see this every time we do one of these ratio tests. And then for the x's, x plus 3 to the power n plus 1 divided by x plus 3 to the power n, those all cancel except 1 remains in a numerator. And so it's just like this, x plus 3 in absolute value to the power 1, right? We had 1 extra upstairs. All right, and then we take the limit. What happens when I take the limit? The 1/4 stays like it is. N plus 1 over n, remember, becomes 1. That's because this is like, you know, well, here, I'll write 2 steps. Like I said, if you're used to doing these, you can probably skip a lot of these steps. I'm going to, in this fraction, divide out by n on the top and the bottom. Make it 1 plus 1 over n divided by 1, right? And then absolute value x plus 3. That thing with the n there just becomes 1 when you take the limit. 1 over n in the numerator goes to 0. Anyway, we get 1/4 times absolute value x plus 3. This is the L. Ooh. Yes. Is that right? That's what I... Yeah. Did I say it wrong? All right. Yeah, it's 1 plus 1 over n over 1. Okay, so this is the L. What does this have to do with the radius of convergence? So I'll just write this again. L is 1/4 absolute value x plus 3. What does this have to do with the radius of convergence? Remember, it converges when L is less than 1. And it diverges when L is more than 1. So it converges when L is less than 1. That would mean 1/4 absolute value x plus 3 less than 1. We can solve this for the absolute value of x plus 3 by just multiplying the 1/4. You multiply 4 onto the other side. I'll say i.e. x plus 3 less than 4. 1 times 4 is 4. And this, my friends, is the radius of convergence. That number 4 is the radius of convergence. What this says is you can think of this x plus 3. Of course, that's the same as absolute value x minus negative 3. And this is the distance from x to negative 3. So what we have here is the center of this power series is minus 3. And it converges when the distance from x to that number is less than or equal to is less than 4. And so the radius of convergence, it converges for all of these numbers which are within 4 of that. So I guess it would go up to plus 1 here and down to negative 7. And it converges for all of these numbers. So the radius, I'll just write it down. Radius of convergence is 4. All right. It converges for all numbers which are within 4 units of negative 3. If you want to say the, we often talk about the interval of convergence. The interval in this example is from minus 7 to plus 1. Now we haven't actually checked the endpoints. We don't know if one or the other of those endpoints is included in the interval of convergence. We could check them if we want to, but I don't want to get into that. All right. Any questions about this so far? And the folks at home, I hope you're doing all right. Great. This is how you find the radius of convergence. Let me just can I just point out a little trick here? The L was 1/4 times x plus 3. Can I just say you're gonna be doing a bunch of these on the homework. If you do it right, oops, change my color. If we do it right, for a series, a power series centered at A, we can get something like L equals, some number here. I'll just put like a K and then x minus A. This is often how it works out. It's not always, but usually you work things out so that you get L equals some number times absolute value x minus A. So in this example, that's what it looked like, right? L equals was 1/4 times absolute value x plus 3. And actually, we did some examples last time. If you look back at those examples, you'll see the exact same thing happened. We always got L equals some constant times absolute value of x minus A. In this case, the radius of convergence is equal to 1 over k, right? In this example we just did, it was a 1/4 in front there, and so that means that the radius of convergence was 4. In general, if you get some number in the front here, that number is the reciprocal of the radius of convergence. This is usually how the examples go. Not always. This is not a hard, fast rule. Like sometimes actually you might get an exponent right here. It didn't happen in this example. That would change the effect of this slightly, but this is what most examples are going to look like. Okay, this is how to find the radius of convergence of a power series using the ratio test. Any thoughts about that before we go on to another little something? All right. What I want to talk about today, sort of our main topic for today, is going to be the power series of a function. So far we've been talking about just sort of power series on their own. You know, I give you a power series, can you tell me something about its properties? But it turns out sometimes a power series is equal to some other function which doesn't look like a series, but just like an ordinary function. Sometimes a power series equals some ordinary function. And we've seen one example of this, and that was actually a very important example. And kind of everything we talk about today is going to be based on this particular example. Just the sum of x to the power n, which looks like, if you write the terms out, would look like that, right? We talked about this example last time, maybe even the time before. This converges. This is a geometric series, right? Where the r is x and the a is 1. I actually want to write down what I just said. This is geometric with r equal x, a equal 1. Right, because geometric means if you divide any one by the previous one, you get the same answer every time. And that's true in this example. Any one of those terms divided by the previous one, the answer is x, and that's the r. And then the a, remember, was just the first term in the series, which in this example is 1. So this is a geometric series with r equals x and a equals 1. And so it converges if absolute value x less than 1. So actually you can see right away the radius of convergence here is 1, because it converges when the absolute value of x is less than 1. So if that's true, it converges. And in fact, just because we know something about geometric series, we can say what it converges to. It converges to this, 1 over 1 minus x, right? It's a over 1 minus r, which in this particular example is 1 over 1 minus x. So what that means is this sum, n equals 0 to infinity, x to the n, is equal to this other function. This is what I meant when I said at the very beginning. Sometimes a power series equals some ordinary function. Here is the standard example of this phenomenon. On the left of the equal sign, we have a power series, but it turns out it's the same. It is equal to that thing on the right, which is more or less a normal-looking function. All right? These are equal. I will just reiterate here. These are equal only when absolute value x is less than 1, right? If it doesn't converge, it's only equal when they converge, when the one on the left converges. The right-hand side, actually, you can plug whatever x you want into it, and you'll get an answer. But the left-hand side, you can only get an answer when the absolute value of x is less than 1. So this, you could say this equal sign here is only valid when absolute value of x is less than 1. But in that case, then the series is equal to that other function. All right? We say in this, like in this example, we call this the sum x to the n, where n starts at 0. Or I'm going to say, we say that this is the words for this is a power series representation of 1 over 1 minus x, right? 1 over 1 minus x is an ordinary function, but you can write it instead as a power series. And it has a radius of convergence equal to 1 in this example, because it converges when the absolute value of x is less than 1. And the interval of convergence in this example, interval of convergence, is the open interval minus 1 to 1. This is just because we know in this particular example, if x actually equals 1 or negative 1, it does not converge. You can check that. All right, the interval of convergence is minus 1 to 1. Okay, everything that we're going to do in this section is about finding the power series representation of some other functions. All right, so this function right here, it has a very simple power series representation. What if I give you a slightly different function? Can you find me a power series for another kind of function? Well, we'll see. The answer is yes, it is possible to do that. How about, let's try 1 over 1 minus 2x, all right? Can I find a power series representation for this? Find a power series and say the interval of convergence. Would you mind? I'm just going to say IOC for interval of convergence, just so I don't have to write that phrase over and over again. Find a power series and say what the interval of convergence is. This is what we're going to talk about for the next little bit, is a bunch of simple tricks to find power series for other types of functions. So the idea is we remember, you basically just memorize this simple example, right? And you plug stuff in, or you make substitutions, okay? So in our example, ours is the same, but with 2x instead of x. All right? And so we are going to just plug 2x into this power series, the simple one here. Just change the x's into 2x each time. All right, so I'm going to substitute 2x. So 1 over 1 minus 2x is the series, n equals 0 to infinity. And then instead of x to the n, it's 2x to the n. All right? Now, to write this, this is basically the answer. This was a very simple one. To write this as a power series, really what we want to see is some stuff times x to the power n. So I'm going to simplify or expand, I guess, this so that it looks like that. Because when I see a power series, I want to see what are the coefficients and then times x to the power n. So this is a power series where the coefficients are the powers of 2. And if I were to write out a few terms here, it would be, the first term is a 1, because when you plug n equals 0 there, you get 1. But then I get 2x, this is 2 to the power 1. Then I get 4x squared, 8x cubed, etc. This is the power series for 1 over 1 minus 2x. You just plug the 2 in where the x used to be. All right? And what about the interval of convergence? For the interval of convergence, remember the original thing here, the interval of convergence was the absolute value x has to be less than 1, right? And so it's, in this simple case, the interval as an interval, that's the interval minus 1 to 1, right? In my more fancy example, it's the same thing, but I have to use 2x instead of x. So for the interval of convergence, it's that, right? And now what you have to think about, what interval does that represent? I mean, this is where you start, but you need to figure out what is the interval for that. Well, first of all, I can simplify a little bit the absolute values on the right. That's the same as this, because 2 is positive. So absolute value of 2x is the same as 2 absolute value x. You can always factor a constant out of an absolute value, although if the constant itself is negative, you turn it positive. Anyway, less than 1. And then I can write x is less than 1/2 in absolute value. And so this is the open interval from -1/2 to +1/2. That's what this means. So the interval of convergence is the interval -1/2 to +1/2. All right? These are the numbers for which the absolute value is less than 1/2. That's my interval of convergence. All right? And that's how we do it. So this particular example was a simple trick in which you see here I had 1 minus 2x. I know how to do it for 1 minus x, so we just plug 2x instead of x for everything. That's all there is to it. All right, that was a simple one. Let's try some slightly fancier ones. How about the sum n equals 0 to, what? No, I give you the function, you give me the series. What about 1 plus x? The standard format that we already know is 1 over 1 minus x, and we want to somehow do substitutions or something. The strategy here is make it look like 1 over 1 minus some stuff, right? That's the idea, because that's the format that we already know. Can anybody say, how do I transform that? This is actually equal to 1 over 1 minus something? Yeah, how about 1 over 1 minus negative x, right? And then from there, we plug negative x into the standard geometric series format. So we're going to plug minus x into this sum, right? The sum of x to the n. Just like in the previous example, we plugged in 2x everywhere. This time we're going to use negative x everywhere. So we get 1 over 1 plus x is the sum, n equals 0 to infinity, of minus x to the n. And like I said before, I like to see this in terms of some stuff times x to the power n. So in this example, when I split it up, it's going to be like that. Minus 1 to the n times x to the n, right? And if I were to write out a few terms of this series, what would it look like? The first one, using n equals 0, would just be 1 times 1. When I use n equals 1, I get a minus sign. So it's 1 minus x, and then plus x squared, and then minus x cubed, and then plus, etc. This is alternating signs, powers of x. So that is the power series for 1 over 1 plus x. And what about the convergence? Remember the original geometric series, it converges when absolute value x is less than 1. This time I used minus x instead of x, so I should say absolute value minus x is less than 1. All right? But when I factor the minus sign out of the absolute value, actually absolute value minus x is just the same as absolute value x, right? So in this case, the interval of convergence is the same as for the ordinary geometric series. So the interval of convergence equals minus 1 to 1. That's the interval of convergence in this example. All right. I got more simple tricks. Let's try another one. How about more simple tricks? 1 over 2 minus x. How you like that? 1 over 2 minus x. Again, I want to try to force it to look like, make it look like 1 over 1 minus some stuff, right? Anybody got a suggestion for that? How can we do do some simple manipulations to make it look like 1 over 1 minus something, rather than, I don't want a 2 there, I want a 1 there. Yeah, what do you think? Yeah, how about we somehow divide a 2 out? Now, you can't just divide the bottom by 2 just sort of for fun. But you can factor out a 2 from the denominator. That's how I would say it. Factor out 2 from the denominator. I think this is what he meant. Factor out a 2 from the denominator. What I mean is 1 over 2 minus x. I'm going to write it as like that. 1/2 out front, and then times 1 over x minus 2. This is what I mean by factor a 2 out of the denominator. And then you do this series for this part, and then you just multiply the entire series by 1/2 when you're done. That's the idea. All right, let's see if we can do that. So the series, I just leave this 1/2 out front, and then I do the series for the part which is in parentheses there, which is the standard geometric series format, but I use x over 2 instead of x. So it's going to be sum n equals 0 to infinity, and then here it's going to be x over 2 to the n. All right? And then I can shove the 1/2 back inside the series. So this is the same as the sum 1/2 x over 2 to the power n. And as I usually do, I'm going to separate out the x to the n part from the rest of it. And so when I do that, it'll look like 1/2, and then you could say 1 over 2 to the n times x to the n, right? If you separate, do the nth power in the numerator and the denominator, and then separate out the denominator, because I like to see some stuff times x to the power n. And then actually this you can simplify very slightly by just combining the 1 over 2 times 1 over 2 to the n gives me 1 over 2 to the n plus 1, right? You get just an extra 2 on the bottom. This is the power series. It's not 1 over 4 to the n. It's because when you multiply, when you go 2 times 2 to the n, you think of this as 2 to the 1 and you add the exponents. That's, if it were that, then this would actually be 4 to the n, but the parentheses, in our situation, the parentheses don't go like that. So it's not this. Yeah, great. It's a good thought, though. All right. This is our series. So if I usually like to write out a few terms. What would this look like if I write out a few terms? So when I use n equals 0, it'll say 1 over 2 to the 1, x to the 0. That's 1/2. And then the next one would say 1 over 2 to the 2. That would be 1/4. And then x. The next one would say 1 over 2 to the 3, which is 1/8 x squared, etc. These are a few terms of the power series. All right, what about the convergence? The interval, the standard power series would say absolute value x is less than 1. In this case, I used x over 2, so I'm going to say absolute value x over 2 is less than 1. One thing to notice is that extra 1/2 that we pulled out actually has no effect on the convergence, because originally that extra 1/2, which is out here, it wasn't even part of the series. So this extra 1/2 should not come into play when you're computing the interval of convergence. It's only what was inside the series that matters. What do we get here when we solve for absolute value x? I think it's going to say absolute value x equals 2, right? You multiply that 2 on both sides. Absolute value x equals 2. And so the interval is the interval from -2 to 2, right? The interval of convergence is -2 to 2. There you go. I got 2 more, and then I have some for you all to try. These are all sort of simple tricks you got to learn about. Plugging stuff into the to the series. This trick was about adjusting this number here. If this number is not a 1, you have to do this trick, which we just did. All right. What about other scenarios that may occur? How about something like No, we start with the function x over 3 minus x. What are we going to do for this? Actually, this is a similar one. You should, when you look at this, you should identify two things that kind of need fixing. One is the 3. We would like for that 3 to say 1. And the other is the x in the numerator. We would like for that x in the numerator to be a 1. That's actually easy to deal with. The x in the numerator, we can just sort of factor it out front, right? So I just say this is x over 3, x on the outside times 1 over 3 minus x. So that deals with the numerator, no problem. And then I'm also going to factor 3 out of the denominator like we did in our previous trick. So it will end up looking like x over 3 times 1 over 1 minus x over 3, like that. All right, and now we're ready to write our series, and then we can multiply the x over 3 back into the series after we write the series. So it's going to be x over 3 times the sum, n equals 0 to infinity, x over 3 to the power n, right? The standard geometric series sum, but with an x over 3 instead of x. And then we reinsert that extra factor of x over 3. So it's going to be x over 3 times, and I will, like I usually do, separate out the x to the n's from the rest of it. Come on now. Sorry, I don't know why that. Here we go. You just have to do that every so often. You gotta let it do its thing. If I put this all together on the inside, it looks like the sum. Those 3's will combine, give me 3 to the power n plus 1. And actually, the x's will combine, give me x to the power n plus 1. So it's 1 over 3 to the n plus 1, x to the n plus 1. From n equals 0 to infinity. That's how it goes. All right, this is our series. If you want to write out a few terms, let's say the n equals 0 term, you get 1 over 3 to the 1 times x to the 1. So this one looks like 1/3 x. The n equals 1 term would look like 1 over 3 squared times x squared. That's 1/9 x squared. Next would look like 1 over 27 x cubed, etc. All right. So this series actually doesn't have a constant in the front of it. It just begins immediately with an x term. Okay, and what about the interval of convergence? Convergence. This is similar to the example that we just did. Remember, you don't care about that stuff which we left outside of the series. All that matters is what you had in this position right here, because that's the only part which was inside the series when we started. So for the convergence, I say absolute value x minus 3 is less than 1. And then multiply the 3 over, we get absolute value x less than 3. And so the interval of convergence is minus 3 to 3. All right. This one was not terribly different from the previous one we did. I got one more, and then I have some for you to try. Let's try x over 1 minus 2x squared. The x on the top is just kind of window dressing, right? This we factor out, and we make x over x times 1 over 1 minus 2x squared. That's really the only trick which is necessary. Now we do the series for that fraction using 2x squared instead of x in the standard geometric series. So I have x on the outside, sum, n equals 0 to infinity, 2x squared to the n, like that. 2x squared to the n. And when we kind of simplify this, well, first of all, you can put the x back in, and then doing that nth power gives me a 2 to the n, and also a x to the 2n, right? X squared to the n is x to the 2n. And we can combine with one more x. These sums are all n equals 0 to infinity. Multiplying the one more x on gives me 2 to the n, x to the 2n plus 1, right? And that's our series. And so this time, if I were to write out a few terms, it would look like, so when n equals 0, 2 to the 0 is 1, but then I get x to the 0 plus 1. So the first number is, or the first term is just x. N equals 1 gives me 2 to the 1 times x to the 3. N equals 2 gives me 2 to the 2, which is 4, times x to the 5. Then I get 8x to the 7, etc. This is a weird pattern. The coefficients are powers of 2, and the exponents are the odd numbers. Right? Yes? Sure. Yeah, you don't have to ask me. I appreciate the respect that you show by asking. Okay. All right, what about the convergence? So this example is not all that different from the previous ones, although the convergence is a little bit more interesting. For the convergence, as we always say, absolute value of x less than 1, but in this case, instead of x, I used 2x squared. So this time it's going to say absolute value 2x squared less than 1. And now this is a little more interesting to solve this for x, which I mean absolute value x, because when you sort of simplify the absolute values, this is the same as that, right? 2 absolute value x less than 1. Then I can divide by 2, gives me absolute value x squared, this way, absolute value x squared less than a half. And then we have to take a square root, which makes this a little, I don't know, a little more interesting. Absolute value x less than 1 over root 2. And this is our interval of convergence. So the radius of convergence is that number, 1 over root 2. The interval is minus 1 over root 2 to positive 1 over root 2. That's the interval of convergence. All right. So sometimes you got to do a few extra little things at the end to find the interval. That was what this example was supposed to demonstrate. Okay, great. I got some for you all to try. I have 3 for the folks in the audience. How about 3 over 2 plus x, x squared over 1 minus 3x. I was doing its thing again. 2 over 1 plus x squared. See what you think. So your job each time, I will say, find the power series. Let's say write out a few terms, like I do, and then find the radius and the interval of convergence. See what you think. You gotta make sure you use the right tricks for each scenario. Any questions from the folks at home? Everybody doing okay so far?
Doing good.
Okay, thank you. Any questions from the Zoomers? Hope you're doing it. Let's take a few more minutes and then we'll go over them. I know probably not all done. That's all right. All right, let's chat about these. I know it's all right if you haven't finished them all yet. This is what I got for the first one. You should factor out 3 over 2, turns it into 1 over 1 plus x over 2. The fact that this is a plus right there means that you're going to have to use negative x over 2 as the thing that you plug into the series. I hope you used the minus sign there. All right, and so what I got when I plugged everything in and simplified stuff was this format here. How exactly you decide to group together the various constants is kind of up to you. But if you write the terms out, I hope I did this right. These are the terms that I got. I wrote the first 4 terms. All right. Any questions about that? I hope this is similar to what you got. And then what about the convergence? For the convergence, we say x over 2 less than 1. Actually, negative x over 2 in absolute value is less than 1, but the negative ends up not mattering. We multiply the 2 to the other side. It'll say absolute value x less than 2. And so the interval of convergence is minus 2 to 2. All right. I also said find the radius of convergence. Well, this is an interval where the middle is 0 and it goes out 2 in either direction. So the radius of convergence is this number right here. The radius of convergence is 2, right? That's that. Anybody got any thoughts about that? This is that first one. Okay, great. Let's just try and go through the other two. So the second one was x squared over 1 minus 3x. Your strategy for this one should be to factor out the x squared. And then I have 1 over 1 minus 3x, which becomes x squared times the series of 3x to the power n. So this is the series. This thing's not doing well this morning. I'm getting a new computer soon. 3 to the n, x to the n plus 2, I think is what I get when I split up the exponent to the power n, but then I have 2 extra x's from the outside that come on in. 3 to the n, x to the n plus 2. So if I were to write out a few terms here, I would get the first term is just x squared, and then 3x cubed, and then powers of 3 on the front. 9x to the 4, 27x to the 5, etc. etc. Right? These are the terms of the series. And then how about the convergence? You say absolute value 3x less than 1, which means absolute value x less than 1/3. So the radius of convergence, can I just write ROC, is 1/3. And the interval of convergence is minus 1/3 to 1/3. I hope that's what you got. Anybody got questions about that one? Is this one easier than the previous one? I don't know. Okay, and then the very last one is also maybe the easiest. I don't know. The last one is also easy. So it's 2 over 1 plus x squared. Maybe that first one was harder than the other ones. This one, you can just factor the 2 out of the numerator. Make it 2 times 1 over 1 plus x squared. And then this one, when you turn into the series, the thing I'm plugging in is negative x squared to the power n. Right? Because the original fraction has a plus in it, means when I plug in, it has to come in as a negative. And I take the x squared with it. If I were to simplify a little bit, this becomes just minus 1 to the n times 2, just a single 2 from the outside, pushing it back into the series, and then x to the power 2n. So we have alternating signs. The coefficient is always 2, and then the x is just only the even powers. So it would be, the first term is positive, so 2, and then minus 2x squared plus 2x to the 4 minus 2x to the 6 plus, etc. It's 2 every time, and even powers of x and alternating the signs. All right. And so, what about the convergence? Interval of convergence. I'm going to, we do this, right? Absolute value minus x squared less than 1. The minus will go away when you do the absolute value. What remains is just absolute value x squared is less than 1. Take the square root. Actually, we're still going to get 1. So absolute value x less than 1. So the radius of convergence is 1, and the interval is just the open interval minus 1 to 1. In that case, the square really didn't have any effect on the interval. All right, I hope you got those, something like that. Any questions about any of those? Simple tricks, really, but you gotta sort of remember which trick to use when. All right, great. Let's talk. We got 15 more minutes. We can say a little bit more. What about other kinds of functions? So all of this basically will work. We can do stuff like, I don't know, one thing over something plus or minus something involving x, right? Basically, all the tricks that we've talked about so far, I'm not trying to be very specific at this point, but vaguely speaking, those tricks can apply to anything that has this basic format. That's still quite restrictive. Like, eventually, I would like to talk about, can we just find the power series for anything? Certainly, there are many, many functions that don't look like this. What about other functions? Of course, there are many, many other types of functions. I'm even imagining things like sine and cosine. You find power series for anything you can imagine, right? What about other functions? There are some simple tricks to use for other kinds of functions. And there's also a general purpose method that we're going to talk about eventually, although not today. But we can get more functions by doing some weird tricks involving integrals and derivatives. So more power series can be constructed by taking, or I'll just say doing, derivatives and antiderivatives. One very, very nice thing about a power series is that it's easy to take the derivative of a series, of a power series, right? If you have something like this right here, anybody can tell me what its derivative is. You just go, from left to right, you just take the derivative of each term, all right? That's easy to do. In fact, it's much easier than taking the derivative of the original function, right? In this case, the original function was here. Now, we know how to take the derivative, but it's kind of a pain, all right? Maybe you would use the quotient rule here, or you could write it as a -1 power and use the chain rule. But in any case, there's some kind of complicated stuff you'd have to do to find the derivative of that as written. But once you write it as a series, the derivative and the integral also become very easy. This one, actually, the integral is quite difficult. I'm not sure.
Wait, quick question about that.
Yeah.
Isn't 1 over 1 plus x squared, if you take an integral of that, isn't it like tangent or something?
Yeah, that's the arctangent, I believe. So actually,
So wouldn't it be 2 arctan, or you could
yeah.
just be arctan?
No, you're right. The antiderivative of this one.
Yeah, you can take the integral and turn it into arctangent, or it would just be arctangent, because the 2 would go right, it's constant, right?
The 2,
Or
it would stay as a 2. It would be 2 arctan of x. Yeah. So actually, this is a case in which the integral turns out to be easy to do, but that's kind of coincidental, right? Or it's sort of getting lucky. Right here, the integral of this is not easy, and I'm not sure what you would do to find the integral of that. I guess I would do a long division and then do partial fractions. But you could pull the 3 out. That wouldn't help to do the integral, though, because of the x squared on top is what makes it hard. Anyway, I'm trying to say the original function may be difficult to find the derivative or the integral, but once you write it as a series, this is easy to find the derivative or the integral if you just go term by term. Now, you might be suspicious. Can I really, in an infinite sum like this, can I really find the derivative by just doing the derivative of each term? Or is there some funny business that occurs because of the infinite nature of the series? It turns out, actually, that there is no funny business, but this is really, it's not obvious. I'm going to write this as a theorem. And the theorem just says, you are indeed allowed to take the derivative of a series by going term by term. So the name of this theorem is called term by term derivative and integration. And what it says basically is just, yes, it is legal to take the derivative term by term. So here's what it says. It says if f of x is a function, but it has a power series, it looks like cn x to the power n. So if this is a power series, then f prime of x, the derivative of the function, also has a power series, and the power series of the derivative is obtained by taking the derivative of the power series. So if this is a power series, then the power series for f prime, the derivative, is f prime of x equals, and what I'm going to do is just take the derivative of the series, and it will look like, when I do derivatives, it looks like this, right? Cn times n x to the n minus 1. That's the derivative of x to the n. So if you have a power series for a particular function, then the series for the derivative is easy to find. You find it by taking the derivative term by term. That's why this is called the term by term differentiation and integration. All right? So that was about the derivative, and I'll say and similarly, the integral f of x. I'm going to put, well, I'll say it this way, dx equals, as we all know, the integral, when you do the antiderivative, you always get an extra constant. So you get some extra constant plus, and then the series, the power series for the integral is Cn times 1 over n plus 1 x to the power n plus 1. This is the integral, term by term. These, of course, are all sum n equals 0 to infinity. You can find the derivative using the power series, and also the integral using the power series. All right. So let's do a simple example of this. How about let's take derivatives of the standard geometric power series, right? 1 over 1 minus x on the left is equal to that series on the right. What the theorem says is you can take the derivative of both sides and it'll still be equal. So if I take the derivative on the left, let me call this f of x, although they're equal on both sides. But when I write f of x, I mean just the ordinary formula. What is f prime of x, the derivative of f of x? How would I find that? Well, you could use the quotient rule here, or it's probably better to just write it as 1 minus x to the power negative 1, and then do the chain rule. To me, that's better than doing the quotient rule. So I'm going to say f prime of x is the chain rule, minus 1, minus x, minus 2, and then times the derivative of the inside, which is negative 1, right? Derivative of 1 minus x is negative 1. If we simplify all that, the minus 1's cancel, and I just get 1 minus x to the negative 2. I'm going to write that this way. That's what the negative 2 power means. All right? But the theorem says that this derivative is equal to the derivative of the series term by term. And so this means 1 over 1 minus x squared is equal to the derivative of the series, which is, remember I started with the sum just x to the n, right? And when I take the derivative term by term, it becomes the sum n x to the n minus 1. Now, something slightly weird about this, and that is that the constant goes away. Sorry, I should have said up here, as part of this theorem, this is a mistake that I made. So the sum here, it starts n equals 1. Sorry about that. It's because when you take the derivative of a power series, whatever used to be the constant in your original series should go away entirely. So what used to be like the constant c sub 0 should not be part of the new series at all, because when you take the derivative, the old constant goes away completely. And so we need to start the summation at n equals 1 instead of n equals 0. Sorry about that. The integral is still correct. You should still start at 0. The problem with the integral is not that the constant goes away. The constant stays, and you need to insert a new constant out of nowhere. That's where the big C, that's why there's that big extra C in the beginning. All right. So anyway, I realized I messed it up when I got to here. This, what I wrote at the very end here, should not be n equals 0 to infinity. It should be n equals 1 to infinity. All right. And if I were to write out a few terms, what would it say? N equals 1 gives me 1 times x to the 0, so that's just a 1. And then n equals 2 gives me 1 plus 2x plus 3x squared, 4x cubed, right? Each time we see n as the coefficient and n minus 1 as the exponent. All right, anyway, and this equals 1 over 1 minus x, the whole thing squared. This is a new kind of power series, which is not, you can't get that by doing simple tricks like we were just doing before. You know, those examples that we were doing 10 minutes ago? Those tricks do not suffice to find this kind of power series. The way to get this one is by taking the derivative of the other one. All right? This is what I meant when I said sometimes we can find new power series by taking derivatives and integrals of ones that we already had. All right? I have one more example, although it's quite a bit fancier than the one I just did, so maybe I'll leave that until next time and let us go a few minutes early, if that's okay. All right, so I hope you have a good weekend. We will have homework due. I'm going to post it later on today. See you next time.
Thank you.
Mm-hmm.